All right. Okay, so hi, I'm Anna.
I'm Daniel, and we're going to be presenting our ASL gesture recognition project.
So the goal of this project is to create a neural network that, given an image of someone signing a letter from the American Sign Language alphabet, to classify which letter of the alphabet it is. So the motivation for this is to be able to bridge a gap between the deaf community and the hearing community, as isolation is a very real sentiment that is felt within the deaf community, and also to build kind of a building block for further implementations of such a device. So this is just an example of the input, and this is the output we would hope to get.
So how we envision our software working and kind of how it works right now is you input a file path to a file you've already taken where you're signing something. The main file will then pull that file from the image data and send it off to processing, so that will just require it to filter the images and resize them as well. And then it interacts with the model to get a classification output and outputs that prediction back to the user. So our source of our data set was mostly from Kaggle. So a Kaggle data set was collected by one person, and that contained about 87,000 training examples. So that's 3,000 examples per class with 26 letters and 3 punctuation. Then we used some image processing techniques to filter, enhance, and whiten those images to extract a little bit more about the features that are actually relevant. And then we collected some of our own data to test for generalization after our model was trained.
All right, so I'm going to talk about the data pre-processing. So we used filtering, so this is just an example. So here we have kind of an example from the original Kaggle data set, and you can't really differentiate the finger, so it's kind of hard to see what he's signing. Here we applied some filters, so adjusted the brightness, the sharpness, and the contrast. And here we used the whitening technique, also called ZCA, or zero component analysis, which essentially removes redundancy and decorrelates features, so that when we're running it through the net, it can kind of learn the structure of the image more. So it basically sets the covariance matrix to identity and the mean to 0. And here is just combining these features along with edge enhancement, so we can even more clearly see the edges. So the data collection, we collected our own data test sets. We took pictures of our own hands signing the ASL alphabet under different environments, so different lighting, use of non-dominant hand and dominant hand. And we did this so we can kind of test for how well the our neural net generalizes. And then we labeled, processed, and put them into test sets and kind of put them into our model. So this is just an example.
So our model is a convolutional neural net because this is the task of image classification, which just consists of 2D convolutions at first with conventional max pooling and some dropout there to add to reduce overfitting. We feed those into some linear layers and with Rayleigh activations to eventually output into our classes. Our model is actually pared down from our original design just because we found that larger model wasn't actually training at all in about 45 minutes of training, and that our small models were training and had fairly good results for the time that we trained it for. So this is the example of the model that we're currently using. So it's just you input the image with 3 channels, so it is RGB. You have one convolutional layer with 10 kernels, another one with 15, and then feed it into a 2x2 max pooling. A 25% dropout we found was pretty good for reducing overfitting, and then fully connected nodes that would eventually output into the 29 classes. So our first working models, they achieved about 20 to 30% accuracy, but they tended to overfit quickly. So as you can see here, after about 20 to 30 epochs, there's a much larger divergence of the training accuracy and the validation accuracy. So kind of just remedy this, next slide, we go into just increasing the number of samples we're taking per class. As I mentioned before, there are 3,000 samples per class, but that's too many to actually load into our computer or the cloud without increasing the amount of RAM that we have. So we just note that just by increasing the number of samples, we can increase our accuracy by a significant amount, about doubling it, just because our model is learning from more sample variation, and that's helping it generalize as well. So then when we apply image filtering, we actually see that our model improves drastically. So we're getting about 61.5% validation accuracy. And that's around after 15 to 20 epochs. And that's the kind of the model that we're going to be looking at the test set for. So on our test set, which is just the Kaggle data set, so the images that it was trained on, similar ones to that, it's from about 60%. However, on the data that we collect, it's about 25.5, and that could probably be a result of the different lighting conditions, environment, and also resolution of the photo, despite the fact that we do rescale it.
So this is an example of our model working on our test set. So this is a typo, it should be the letter A. So here we input the letter A, but it outputs the letter S. And when we actually investigate the tensor that it outputs, we see that we're taking the argmax to get the classification. So here's 15.3, it's the highest number, and that corresponds to letter S. But the third highest number, which is 14.7, corresponds to A, and we see it's much higher than the general numbers. And even though our model isn't working great, when we look at the letter S, we kind of see why it predicts that. So even though it's not working great, we might be able to use different models together to kind of fix this kind of stuff. So for example, looking at sequences of letters within words and maybe using a recurrent neural net with this. And here's an example of it working correctly. So here we have the letter B, and it correctly outputs the correct prediction.
Some of the key learnings that we had here. So the importance of data preprocessing and its effect on accuracy. So basically, by extracting further features from your data, so image data, applying enhancement techniques, whitening techniques, and such like that, you're going to get better features for your model to train on, which is going to help it kind of identify what's key in the photo and what's kind of the noise that you don't really care about. And then higher accuracy, just feed in more data as well. And then when you're coding, just pay attention. We made a lot of those mistakes in the beginning. It could have been remedied and saved us a lot of time if we just paid a little more attention to the details. Thank you.
Great, really interesting project, and you can see how it could lead to something really useful. It was interesting to see the difference in the pictures from Kaggle and your pictures. The lighting was completely different. That's why you were getting really different answers. Why are their pictures so bad?
So the photos that seem to be, I played them like in sequence by just like pressing next really quickly, and it seems like he just took them from his webcam and just moved his hand around slowly and took the frames out. Whereas we used webcam/phone, so I think we just had inherently better lighting. So that might be a reason that when we're processing our images as well, maybe perhaps whitening them and such, it's not extracting the same types of features that get extracted from the darkened image that from the original training set.
So that explains how that person produced 87,000 images.
Yeah.
Too,
Yeah.
That makes sense actually. I really like what you did, by the way, with the error analysis. That's a really good. I'm going to somehow throw that into this course next year to find some way to get people to pursue that. I think that's key. The last question. This attention to detail. What do you mean exactly? Like programming errors?
So we can.
What do you mean?
If I had paid a little more attention to the tutorials we'd done, so I just got complacent in terms of we'd done a few convolutional notes in the past. Then okay, let's just go into this. But I forgot to actually load my data in as floats and not integers. So basically I was dividing by 255, but that was actually just straight up and normalizing them. So that was straight up just cutting half the values to like 0 and then half to 1, or like a lot less than that to 1. And I was wondering why my model isn't training well and why the gradient a lot of the time was just 0. And that's basically the reason why is it was just integer dividing it down to 0 for basically almost all the features.
Yeah, that stuff is easy to do, and unfortunately you don't get a flag error.
Yeah.
So another interesting question is how you find errors like that. What other questions? Errors.
Yeah, I mean, I think you asked a lot of the questions I wanted to ask. I guess one thing about looking at the performance of the model, I guess having like a confusion matrix will probably be good to like sort of show that how similar different like letters maybe are to each other. And I guess we're also reporting like say top 3 accuracy, something that people kind of do for like object detection as well or whatever. So like you can show top 1 is on like 61%, but if you do like top 3, then maybe it's now like 90% or something.
Yeah. And when we were looking at our test set, we saw like usually like the ones it misclassifies, they kind of make sense. Like for example, like the N is like this and M is like this, so they would get misclassified a lot.
But yeah, confusion matrix would be great for that.
You said on one of your slides that you excluded the letters J and Z or something like that. Why did you do that?
So the reason is because they actually like require movement. Yeah. So I don't know how the Kaggle user did it. So I just said, okay, I'd rather not do it wrong. When I was doing the test set, I'm like, okay, I can mirror these images, but I don't want to mess up doing J and Z.